So we're going to be thinking about quantum mechanics, quantum chemistry, and all that we've been reading about in chapter 6. And the phenomena that we're going to be introducing this material with really is the absorption and the emission of energy, or what we think of in terms of our visual acuity as the sight of colors. And so have you ever wondered what it is that makes something bright versus what makes something dark? So this all connects to the way that energy is absorbed, reflected, and transmitted. So we're going to come back to this in just a little bit, but as you're wondering, I want you to think about the following. Why is it that you can see all of these colors? And what is it, right, that results in the dark bands that separates some of those colors? So as we're thinking about what we're going to be studying for chapter 6, we're going to be able to describe what an orbital is. We're going to know the number and names of the subshells in each of the first 4 principal energy levels. We're going to be able to know the number of orbitals and the electrons in each subshell. And then we're going to describe how shielding and penetration and multi-electron atoms cause subshells or sublevels within a principal energy level to have different energies. You're going to be able to list the subshells of a given n in order of increasing energy, and you're going to be able to draw correct orbital diagrams for elements and simple ions. So your goal should be to do at least one of these per day, where you're asking questions, defining problems, analyzing and interpreting data, constructing explanations or designing solutions, and engaging in argument from evidence. My guess is that you probably do each of these multiple times a day. We don't always recognize that that's what it is that we're doing. So if you're in the middle of trying to figure out how both you and your sibling are going to get laundry done today, right, that's a great example of asking questions and defining problems. If you are trying to determine whether or not the money that you brought with you to the grocery store, right, is sufficient to cover what's in your grocery cart, it's a great example of analyzing and interpreting data. And then if you're providing an explanation of why shelter in place is important to your friends and family, that's an example of constructing explanations or designing solutions. And then if you're engaging in argument from evidence, perhaps you're in the process of persuading someone that they want to stay at home and shelter in place as opposed to go out for the sake of keeping everyone safe. So we're going to look at the quantum chemistry of the whole periodic table. But in order to do that, we're going to use some very specific academic vocabulary. We're going to use something known as the Pauli exclusion principle. We're going to talk about electron spin. We're going to describe the Aufbau principle. We're going to take a look at Hund's rule. We're going to draw orbital diagrams, and we're going to practice writing electron configurations. So if we think about our rules for drawing orbital diagrams, orbitals are just the distribution of electrons. It's where we're most likely to find electrons. We always fill orbitals starting from the lowest energy orbital with room available. So this is what we call the Aufbau, which is German for building up principle. A great way to think about this is that typically when we enter a building, we do so on the first floor or the ground floor. It's whatever is the easiest access point. Electrons then fill our orbitals within each of these sublevels with unpaired electrons. And so each electron has a spin, and so we have a tendency to isolate our electrons or keep them separated before we pair them up. And that's, again, because of energy. That's what we refer to as Hund's rule. And then the last piece that we're going to take a look at is that electrons in the same orbital must have opposite spins. This is what we call the Pauli exclusion principle. So we use these little one-sided arrows to represent a single electron. And so we use the direction of that arrow, whether that's up or down, to represent opposite spins. So when we're thinking about filling then our electrons in an energy level diagram, we follow some rules. here are our general rules. And we're going to talk about them so we can make sense of them. So we're adding our electrons in the lowest energy orbital first. So this is our 1s orbital, that's our lowest energy, whereas in this diagram, our 4p's would be our highest energies. Each sublevel, right, so each of these orbitals or sublevels are filled in order of increasing energy. So we're going to fill from the bottom to the top. Then the Pauli exclusion principle says, look, I can only put 2 electrons in each orbital. So in each square box, I can only put 2 electrons. And in order for them to fill that box, they have to have opposite spins. So those arrows have to point in opposite directions. And then Hund's rule says, if I have more than one orbital present at the same energy level, I'm always going to fill those with single electrons before I pair up or put 2 electrons in one box. So our Pauli exclusion principle, let's look at this. If 2 electrons share an orbital, then they must have different spins. So our box represents our orbital. This is where we're likely to find our electrons. And then our single-headed arrow represents our electrons. So if I have only one, then it's a single electron. If I have 2 pointing in opposite directions, then that's a pair of electrons. So how do we represent our electrons at different energy levels? Well, if we have multi-electron atoms, then the electrons that interact with each other are going to cause splitting within the energy levels. So essentially, they're not all going to be at the same energy level. We're going to start to differentiate. Some subshells or orbitals are going to be higher in energy than others. So for example, hydrogen has only 1 electron, so it has no energy difference between subshells with the same quantum number n. This is referred to as degenerate. So orbitals that have the same energy we refer to as degenerate. But if I have more than 1 electron, I'm going to start to see something called shielding. This is mostly observed between atoms that have different n's, right, or different principal quantum numbers. So the 2 electrons in the inner 1s shell of lithium, you can actually see those 2 within the blue. These have a tendency to repel the electron in the 2s subshell. This is the one that's outside of the blue. So the 2 electrons that are closest to the nucleus or within that first subshell tend to shield that electron that is outside that first shell. They shield it from the nuclear charge. So there's a proton that's pulling, and in this case, there's an electron that's attracted to that positive charge. But if I have electrons between that positive charge and another electron, they're likely to repel that outermost electron. So how do the energies of electrons vary then within shells? We're going to take a look in just a moment at electron configuration. A good way to think about that is that it is the distribution of electrons. So where do we find electrons? We typically find them in atoms or ions. And with the exception of hydrogen, all other atoms that we're looking at will be multi-electron ions or atoms, which means that between our nucleus and the outermost electrons, we're going to have some core electrons. Those core electrons will shield our outermost or valence electrons from the nucleus. When we describe our multi-electron ions or atoms, we're going to do so using shells, subshells, or orbitals. And the really cool part about this is that these electrons are going to have different ionization energies having to do with their attraction or the energy between one charge and another charge with respect to their distance. So you won't have to calculate Coulomb's law, but it's important that you understand the concept or the basis for our electron configurations. So each orbital is organized by a number and a letter. The number specifies the energy level. The letter refers to the shape. So here on the left-hand side, I've put the first 2 columns of the periodic table. They are represented by the 1s, 2s, 3s, 4s, where the number 1, in this case, refers to the energy level that's closest to the nucleus. These are also called the principal quantum number, or n. S is the letter that refers to the shape of the orbital. In this case, the shape of the orbital is a sphere. And then the other number, 1, in this case, is the number of electrons. So this is hydrogen, and it only has 1 electron. So we're going to use this code to represent orbitals and the electrons that occupy them. So within the same N, or across the same row in a periodic table, we'll be able to describe the energy of orbitals and electrons. The s orbital electrons tend to be closer to the nucleus than the p orbital electrons. So the electrons are more stabilized in the s orbital than in the p orbitals. Because they're closer to the nucleus, they're held on a little bit more tightly, so they're a little bit more stable. This means that our s subshell energy will be lower than the p subshell energy. Our core electrons then are in filled principal energy levels and filled d subshells. If you're thinking about subshells, those are going to be labeled as S, P, D, and F. Orbitals have different shapes, or another way of thinking about that is that they have different electron density distributions in space. So how do we fill our electron configurations? Well, we always start at the bottom. So in this case, we're going to start with our 1s, and we're going to fill that first. Then we're going to fill 2s, then 2p, and then 3s, then 3p, then 4s, then 3d, then 5s. So how do we fill them? Well, the electron configuration is going to describe the placement of electrons in orbitals. So the s orbitals hold 2 electrons, the p orbitals hold 6 electrons, the d orbitals hold 10 electrons, and the f orbitals hold 14. You can actually create the chart that's on the left here just by writing the first column, numbers 1 through 7, the second column, numbers 2 through 7p, the third column, numbers 3 through 7d, and the fourth column, numbers 4 through 7f. So a simple way to be able to figure out the electron configuration of an element is to be familiar then with the blocks of the periodic table. So I want you to take a look at your periodic table and identify where you would find the s orbitals, the p orbitals, the d orbitals, and the f orbitals. I think one of the coolest aspects of chemistry is that we build knowledge over time. Scientists have been iterating their understanding of chemistry for decades, arguably hundreds of years. This is a great example of an early version of a periodic table. You'll notice this is an issue of Life magazine, May 16, 1949. This was considered big news then, that someone had organized, right, our atoms into a periodic table. But you'll notice that this periodic table looks really different than the periodic table that we use today, which is a great piece of evidence showing that scientists are always innovating. Part of our job is to be flexible enough and adaptive enough that we can take new information and make sense of it. Just like you're taking new information around COVID-19 and making decisions every day about what's best for you and your family and friends, how to keep each of you safe. Well, we do the same thing with our information about chemistry, trying to fit that into a larger framework or pattern of information. So next time we're going to take a look at how to take our electron configurations and create them for each of the atoms in the periodic table. Talk with you soon. Thanks again.